Continuous convolution. Why is it such an important thing? That's right. So what she says is in the Fourier domain, if you multiply in the Fourier domain, then that corresponds to convolution in the time domain, which is spot on. Okay, why is that useful? Multiplying in the frequency domain corresponds to convolution in the time domain. That's true. It actually tells you a lot about a system, what a system is going to do to a signal. Okay, so if you have a little signal, a system, and you know this thing called the impulse response, which we'll get to a little bit later on, then you basically have characterized that system to a large degree, depending on the type of systems. This actually just holds for linear time invariant systems. So if I have the impulse response of a system and I feed it with some input, then I can get the output of that system, yt, and that is equal to just xt convolve with ht, the impulse response of that system. And this holds for a special type of system, which we use a lot, called linear time invariant systems. Okay, why this is cool is because this, if you go to the Fourier domain, it actually tells you what the system is doing to the frequency content of my input. Okay, and so convolution is really useful because it can tell me basically how to get the output of a system if I know its impulse response. Okay, so we'll repeat this for discrete systems in this course, but for continuous systems, this is like an important thing to know. Tell me something else about continuous convolution. So this is the definition. It's pretty weird. You have this you're convolving ht with xt, and that means that I have a h tau and a xt minus tau d tau. What else can you tell me about just that definition? Can I flip it? Can I flip the order around? Yes? Yes. Okay, so that's called commutative. Can I say that word? Commutative. Okay? It means that this is also, you can just flip them, and you have a x tau times h t minus tau d tau, which is just the same as x t convolved with ht. Okay, which is kind of cool. And that doesn't always hold for all operations. Okay, so it looks very stupid here. All operations aren't commutative. We'll actually see some examples of non-commutative operations here. Okay, so that's also just important, and you should just know this. You should also be able to you asked about proofs last time. You should be able to prove that this thing and this thing is equivalent to one another. And for that, you use grade 2 mathematics, okay? And you just change the variable here. So you make a little tau 1, which is some function of tau 2, and you basically just change the variables in the integration. Nod? Okay, I'm going to go very slowly through an example of the convolution. But before I do that, I just want to talk about what this xt minus tau thing is. Like, what does that actually mean? So let's just say we have some example signal here, and it looks like this. Here we've got t, here we've got xt, and it's a little like triangle thingy, goes up and then goes to A here. Okay, let's just say I just want to draw the picture of what that thing is. Okay, so this is xt. X tau would look, let me actually just scribble this out. X tau would look exactly the same, except instead of t we have tau. Okay, so x tau. And here we've got a tau. Okay, what does x minus tau look like? What does that look like? It's just flipped. So whatever happened at the point A now happens at minus A. Okay, so it's just a flipped version of that. Spot on. Okay, that's very ugly. Okay, and now if I add a t to this thing, what happens now? So what if we have x t minus tau? Now just as a reminder, this t it's not a function of t, right? It's a function of tau. So I've added this little t here. What happens now? Okay, perfect. So what he's saying is right. Adding that t in there, it could have been an A or a B, right? It shifts the signal left and right depending on where it is. I can honestly never figure out exactly how it moves. Okay, I mess up right and left. So it's a whole like real struggle for me. So what I always think is whatever happened for instance, in this little example, whatever happened at A, whenever there was an A inside the braces here, that now happens when the stuff inside here is equal to A. Okay? So I always have a little cheat which I'm like, okay, T minus tau, if that's equal to A, okay, then I'll be at that point. So what is the value of tau when that happens? Well, tau is equal to, I take it to the other side, now I'm already confused, T minus A. Okay, so whatever happened where A was now happens at T minus A. So let's just say that's a T minus A. Okay, cool, awesomeness. Whatever happened when the stuff inside here was 0, where's that now on this little axis? Well, T minus tau is equal to 0 when tau is equal to T. Okay, cool. So T is there, okay? And then I can basically reverse engineer that this is what happened now to the signal. Okay, so I always use these little hacks to figure out how it's moving. Okay, everyone happy? I'll just give you a second to scribble. Let's just do a full-fledged example, and then we're done with continuous convolution, and you guys just have it sorted out for the rest of your lives. Okay, so the example here actually has the answer already. The question is, how do I convolve this like triangular thing? So it's 0, 0, go to 2, down to 1, and then stays at 0. I convolve that with this little pulse here. Okay, so what we're going to do is we're going to start by taking the pulse, flipping it, and then shifting it. We're going to flip it and then drag it across basically the triangle. Okay, you guys with me? So let's just quickly repeat what we did on the previous slide. We're going to flip this thing and then drag it across. So we end up with a little function here, and it's a function of tau. Okay, and what we're going to draw here is xt minus tau. Okay, so this thing will be 0, 0, 0, 0. Then it will light up and it goes to 1 there. And then it will stay 1, and then it will go down. And this point here, you can go and convince yourself here. This point is t minus 1, and that point is t. Okay, and that's xt minus tau. Convolution is a little bit weird, right? It's a function of t, right? As I change t, my answer, the thing I'm getting out, is going to change, okay? But the stuff that I'm working with on the inside here of the convolution is in terms of taus, right? So this is equal to, so everything inside here is with respect to this variable called tau. And for different values of t, I will get a different area that I'm summing up through the integration. Okay. So for different, basically if I plug in different values of t into this thing, then I'm going to get different values, and that's exactly what the result here shows us. Okay. So let's just do this quickly. So let's just say our t is equal to, let's just start. Our t is equal to minus 0.5. Okay. Then what we are doing is we're taking this squared thing, we're flipping it, and it's dragging across, and it's at a specific point in time now. It's been shifted to a specific point in time. Time t minus 0.5 is we have our little triangle that's just sitting there. So this is h of tau sitting there. And then we have our little pulse. Now, where is our little pulse sitting? Partially in the triangle. Thanks for the attempt, but no. Okay. Centered at the origin. Good attempt? No. Okay, this is great. You guys are sufficiently confused, so I'm not explaining something that you have before. It's really easy. Okay, so let me explain this to you. So how you figure out where the fudge that pulse sits is you look at this figure here, and you have t is equal to minus 0.5. What is minus 0.5 minus 1? Minus 1.5. Okay, cool. Okay, so boom. So this point here, that point there is now at minus 1.5. Where's the other point? Minus 0.5. Wonderful. Okay. So the convolution, this is what the convolution is defined like. Okay. So for different values of t, you can actually think about this as the output of this is yt is equal to this thing. This is yt. And this is time, okay? So I'm going to plug in different values of t, and then I need to execute this operation for that value of t. We're currently at a value of t minus 0.5, which is somewhere here, minus 0.5. It's somewhere there on the axis. Okay? And what is the value at that time point? What is y of minus 0.5? What is y of minus 0.5? 0, right, exactly. Okay, and how did I know this? I flipped this thing and then I slid it across, but the sliding was like really preemptive, so I'm way on this side, there's no overlap, and the result is 0. Awesomeness. Okay, so this plot here, at 0.5, I'm at 0. Until what value of t will I, so what we're going to do now is we're going to take this box and drag it on. At what point do I get a value that's just about to change to something that's not 0? When t is greater than 0, spot on. Okay, so let's just draw it out. So when we're at 0, right on the edge of 0, then the boxes are touching each other. Okay, so at time point 0, the result of yt or y0 will still be 0. So at that time point, we're at 0. Okay, awesome. What starts to happen now? So as we're moving across, we're going to start to get overlap. So for instance, at, I don't know, let's say t is equal to 0.5, then we are where what someone said was at the origin, I think. This is in terms of, remember the whole thing is in terms of tau, so it's a little bit weird, and we're changing t, okay? So at 0.5, let me just use my cheat sheet for people who don't know what left and right are. T minus 0. Okay, we're at 0.5, so 0.5 minus 1 is minus 0.5, so that's there. T is 0.5, so that's there, so my box is sitting nicely around the origin. Okay, cool. And then my green signal is 0, 0, 0, lights up at 2, and then goes down and like this. Okay, and what is the result of the convolution? We're integrating. Okay, so now we're multiplying this box with the green thing and then adding up the area. And the area is just, what is the area here? So that's the area, okay? And then you add that up and that gives you y at 0.5. It's some value, I can't remember what it is, but it's this point here. Okay, everyone with me? Just not. Okay, so then at t equal to 1, then we've got this situation where, okay, and now the result of that thing is just the area of the green thing, which is half base times height, half times 1 times 2, half times 1 times 2 is 1. Okay, cool. And that's why we get a value there that y1 is equal to 1. Y 0.5, I don't know what that is. Okay, it's some value less than 1. Okay, and then what starts to happen is, as we're moving across, now we get a reduction in the area again, because as we're moving across, now we get smaller and smaller overlaps between my triangle and my red box, until you get to the point where there's 0 overlap between them. Okay. Everyone happy? That was a very slow example, well, slightly slow example of continuous convolution. Everyone satisfied on the inside? Awesome.